Hello everybody, you welcome to my image processing and pattern recognition course. This is a part of my course dealing with segmentation and shape representation. Now this is the whole course content. Here is the detailed content of this part. We start with introduction to image segmentation, then we deal with different segmentation approaches from the literature, which are contour-based approaches, region-based approaches, and dual approaches. We will take as example the active contour segmentation approach. Then we move to the second part of this presentation, which is shape representation. In this part, some geometrical-based descriptors as well as Fourier edge descriptor will be exposed. Our presentation ends up with the conclusion. What is segmentation? When an image is composed of a set of objects and a foreground, segmentation is a processing aiming at identifying the set of pixels belonging to objects or subsets of it. Here is an example of a flower segmentation. As it can be seen, two subsets of the flower are segmented. When segmentation of an object is based on identifying the contour delimiting the object and its foreground, it is contour-based. When segmentation of an object is based on some similar characteristic of its inner pixels, it is region-based. Segmentation can also be dual. For homogeneous objects, which pixels have contrast with foreground pixels, region-based methods can be efficient in separating objects. Here is an example where the object leaves region is uniform, whereas the contour is not identically contrasted with the background. For this example, a region-based approach is more efficient. However, for objects having important and uniform delimitations with their foreground, contour-based methods can be efficient in separating them. Here is an illustration example of a flower segmentation. Contour-based segmentation or edge detectors identify discontinuities between regions. It can be based on identifying high-gradient pixels. We need first to compute a first-order or second-order derivative of the image. Image gradients can be obtained by a convolution of the image with specific kernels, either for computing image gradient or image secondary derivative, etc. Here we consider a kernel key. We make the kernel sweep all the image pixels. In one pixel position, we evaluate the convolution coefficients as the sum of multiplications of the kernel and all corresponding imposition neighbor pixels, as illustrated in this figure. A generic expression of the convolution coefficients is given in the coefficient below. Here is an example of a gradient kernel. As can be seen, we compute a means of 3 gradients for horizontal gradient. Another kernel example is that of pre-width, where the computed gradient is a means of 2 adjacent pixels gradients, as illustrated in the above equation. We can use the pre-width kernel for computing the derivative versus y and the derivative versus x, respectively, as illustrated in the figure below. One well-known kernel is that of Sobel, where the computed product is a difference of 2 adjacent pixels gradients as a way of computing the second derivative of the image, as illustrated in the above equation. We can use the Sobel kernel for computing the second derivative versus y and the second derivative versus x, respectively, as illustrated in the figure below. Another way of computing the second partial derivatives is to combine the second derivative with respect to x and y and sum them. We obtain the Laplacian kernel, which is illustrated above. If we compute the partial second derivatives with respect to diagonals, we get the second Laplacian kernel. If we add now all partial derivatives, we get the third Laplacian kernel. For identifying the edge pixels given these second derivatives, we should identify zero-crossing pixels in image Laplacian, as illustrated in the figure below. Another way of computing the gradient is to apply first a convolution with either pre-width or Sobel kernel. For each orientation of the kernel among the Freeman 8 connectivity, we identify the gradient with respect to this direction. Region-based segmentation looks at identifying similar regions that can be based on a similarity criterion, such as a gray level, homogeneity, variance, etc. Accordingly, similar pixels can be gathered either by thresholding the whole image pixels or by splitting subsequently non-homogeneous regions in the image or by merging subsequently similar regions or both splitting and merging. Thresholding can be global, selecting one threshold for the whole image, or local, depending on the surrounding region, or it can be a dynamic thresholding, updating continuously the threshold. Statistical models can be used for defining efficient thresholds. Splitting is a region-based segmentation, which is descendant method based on the following steps. Define a homogeneity criterion. Test the validity of the criterion on the image. If the criterion is valid, we stop. Otherwise, we split the image and continue running on splitted regions. Splitting generally follows a quadtree, as illustrated in the figure above. Merging is a region-based segmentation where we apply the following steps. We consider seed regions with relevance to some context. We grow these regions with neighbors if satisfying some similarity criteria. The criterion can be gray level or variance, etc. The figure below illustrates merging, where the seed region is a red pixel. Splitting can lead to neighboring regions which are not connected. Splitting identifies homogeneous regions that need to be merged for a proper segmentation. Thus, split and merge is required for an efficient segmentation. A dual contour and region-based segmentation approach, which is applied well in medical imaging, is the active contour approach. In the active contour approach, we keep on moving a deformable closure contour, called also a snake, for segmenting a region for which a gradient description is not efficient. Here is an example of image where neither the background nor the object are homogeneous. Thus, neither region-based nor contour-based approach can be efficient. The active contour, however, leads to satisfying segmentation. In this approach, an initial contour C is deformed for minimizing some energy. Energy in snakes is measured taking into account intrinsic property of the curve C, image characteristics near C, and interaction between both. Aiming at minimizing E snake, which is the sum of E internal and E external, where E internal is an energy associated to the contour such as its length and its curvature that should be minimized, and E external is the energy associated to the image properties on the curve pixels such as gradient and region properties. Reduction of external energy makes the curve closer to the contour in the image, whereas reduction of internal energy makes the curve moving slowly so that we don't miss the contour. Generally, this approach leads an implicit description of the contour, which can be useful in shape representation in subsequent steps. We move now to the second part of my presentation, which is the shape representation. Let a shape G be described with a binary function f as follows. F takes 1 on the shape pixels and 0 elsewhere. Let G, a point of coordinates gx, gy, be the centroid of D. These coordinates are thus given by the equation below. Here are some shape descriptors that can be defined and which are efficient for discriminating a shape, such as histogram of gradients, circularity, rugosity, eccentricity, compacity, compactness, and convexity. Let's start with one efficient shape descriptor, which is the histogram of gradients. By considering the image gradient for each pixel and each direction, we can establish the histogram of gradient for the segmented object. It is a powerful texture descriptor. When it is computed only for pixels in the edge, it is a shape descriptor. Another shape descriptor is the circularity, which measures similarity between a shape and a circle by computing the ratio between area of the shape D and area of a circle of the same perimeter. It is illustrated in the figure and expression below. Another shape descriptor is the rugosity, which can be quantified by deviations in normal direction to the surface of the shape. If deviations are large, rugosity is high. One measure of rugosity is the ratio between a surface and its projection on a substrate of it. Rugosity is S over SP, and S and SP are illustrated in the figure below. Another shape descriptor is the eccentricity, which measures the ratio between the length to the width of the smallest rectangle including the shape, as illustrated in the figure below. Compacity measures the compacity of a given shape. In a 2D, it can be the ratio of the perimeter of the shape to its area. Compactness measures the compactness of a given shape. It can be 4p times the ratio of the area of the shape to its perimeter squared. Its value is 1 for a circular shape. It is given by this equation. Convexity is the ratio between the perimeter Px of the convex contour surrounding the object to the perimeter P of the contour of the object. It is given by this equation and illustrated in the figure below. One important descriptor, which is very consistent, is the shape signature. It is the representation of the radius magnitude along the contour. Here is its expression, where xy is the point of the contour and xt, yc is the shape centroid. A small convenience of this descriptor is that it is not normalized. For overcoming such limitation, we can define the Fourier descriptor. Accordingly, let's consider the outline T of the shape, which is a closed curve described by its arc length S and an origin A. We define a function of T, which is called phi of T, which is the angle between the tangent at the origin A and the tangent at position of length S. T is given by this equation, and it is at its maximum value 2p. This function T is real, continuous, and periodical with a period 2p. Therefore, it can be described by a Fourier series as follows. The set of modules of the coefficients A of k is called Fourier descriptors. They are translation and rotation and scale invariant. One can compare two shapes by comparing subsets of the Fourier descriptors, beginning with the lower order coefficients and then using higher order coefficients. To make the description simple, one can get rid of the Fourier descriptors of higher order, but that can cause much trouble because the new shape described is usually no longer a curve, as illustrated in the figure below. As a conclusion, we have started our presentation with definition of segmentation and identified different segmentation approaches. Contour-based segmentation can be obtained with the convolution of the image by different kernels, where each kernel implements some probes of discontinuities in the image. A review of some known edge detectors such as Sobel, Prewitt, and Laplacian is done. Region-based segmentation has a postulate that the inner region of an object has uniform characteristics. Some ascendant and descendant approaches are reviewed, such as the split, merge, and mix methods. Active contour is based on deforming an initial curve for reaching the contour in the image. In the second part of this presentation, we have dealt with shape representation. A shape representation is a discriminant description of the shape. Many descriptors have been presented. Histogram of gradient is a powerful descriptor unifying simplicity and discriminant power. Some geometrical descriptors used in medical field are presented such as circularity, rugosity, eccentricity, compacity, compactness, etc. Fourier shape descriptor remains the most important descriptor thanks to its normalized value. Its invariance with respect to rotation, translation, and scale change. Please feel free for contacting me for any further details. My email address is below.